So how's everyone doing today? Everyone's awake at this point? Okay, good. Because I chose this spot because I knew you guys would be awake in the morning. So. Awesome. All right, so as being said, I'm going to be presenting on avoiding avalanches through quality weather observation. The reason why I kind of chose this topic this year, and I kind of based it almost at the basics, again like I did 2 years ago, and then build upon that, is because I want to cater to everyone in here. Some of you look at the weather every single morning, and I'm sure there's some of you in here that don't really know how to even look at a weather map just yet. So my goal today was actually to kind of put that all together and give you a decent idea of where you can go for information at home, but then also once you're out in the field, how to look at current conditions and see how those forecasts that you saw at home might be changing throughout the course of the day, and then how you can actually change your plans for the day safely. So again, my name is Rebecca. I've been on the summit for 3.5 years now. My primary role in the summit is as a weather observer. So 24 hours a day, there's one of us going outside and actually observing the weather. So if you were to ever look at METAR code, which a lot of pilots look at, I'm actually the person who's coding that. So when it comes to actually looking at the weather conditions outside, I'm kind of the person to be talking to about that. Besides that though, I'm a big skier, and that's kind of what drew me into the Avalanche community here, not only because I work on the summit of Mount Washington, but because I have an interest in those backcountry events. Now, the Mount Washington Observatory is nonprofit member supported, which makes us very unique in that we can focus a lot on education. So last year I was actually given the opportunity to take my first Area 1 level class. It was probably one of the best classes I've taken recently while living up here, but one of the big things that it did for me was actually show me how much weather ties into making safety decisions in the backcountry. And that was really my motivation behind wanting to do this presentation for you today, because I actually saw that whole connection and really wanted to bring them together. So the first part, why weather? Well, without weather, we wouldn't have snow, and without snow, we wouldn't have avalanche risk. Weather has been a part of our planet ever since the day it was created. It's been shaping our planet and it will continue to. So in terms of everything that we do, it's very important. When you look at the decision-making framework, observe there's 3 parts. You're looking at previous avalanches, you're looking at your snow conditions, but then you're also looking at your weather. So 1/3 of that entire category goes straight to weather, but I feel like it's one of the ones that we don't always look at right away because it's something that we just don't know too much about, and that's what I want to help you out with today. So my goal today is to enhance your understanding and technique of at-home and in-the-field weather observations to better help with your decision-making. So who's an observer? By show of hands in here, who thinks that they're an observer? Okay, let me re-ask this question. How many of you today walked outside and looked to see if it was cloudy, sunny, grabbed a jacket, something like that? Okay, everyone's hand just went up. So you're all weather observers in some way. You just don't necessarily think about it that way. Even when I give programs to my little 2nd graders through a Polycom system, all of them are observers. At one point in your life, you have stepped outside and said, hey, it's snowing out. So luckily for me, I don't have to teach you how to do that. I just have to teach you how to interpret that data. And that's what's really important about weather observation. So this then brings in quantity versus quality. Now you can go online and you can find probably about 1,000 different websites that will give you every possible different piece of data that you want, but do you know how to interpret it? Most people don't, and that's the difference between being someone who can look outside and be an observer and someone who can actually be a quality observer. So during the trip planning process, this is probably one of the most important things, just because before you even step out into the terrain, you're making a decision whether it's even safe to be there or not. If you've already decided for that day that a certain route isn't safe, it doesn't matter what the weather is, you're not going to go there. But once you've decided that it's safe enough to go there, now you have to take into account those weather observations. And the things you want to be asking yourself before you even leave the house is, what are the conditions currently, and what could they become later on in the day? Because that will then play into your in-the-field observations when you start to compare what's going on. So what I tried to do today is actually put together a list of websites, and at the end of this I'll give you my email so you can get all these from me. I want you to be able to go to a certain place and not have to look everywhere across the web to get all the information you need. These particular websites, although they're not the best for everything all the time, they have everything right there for you. So they're very intuitive to use, so you're not kind of slogging through all sorts of different tabs and things like that trying to find the information. It's pretty much just right there for you. So the first one is hpc.gov. Here, the 4 most important things that you can probably find off here is your surface analysis, your forecasting page, your QPF, and then your winter weather. So for your surface analysis, this is going to give you what your current conditions are for the day. So by looking at this, you can see where you have high pressure systems, low pressure systems, Does it look like you might have a frontal system passing over you for the course of the day? Do you think that there's going to be different types of precipitation just by looking at what the current conditions exist in that location? But then when you move forward and you look at your short range forecast, how is that going to change over the next day, over the next 2 days? Because sometimes we're in the field for more than one day. So this is all this data that you have to be collecting before you get on the field, because we all know that our cell phones don't work once we're out there most of the time. So now we're going to look at how is that system going to progress. If there was a low pressure sitting off to the west of us, is it going to progress through overnight? Is it going to come through faster in the day? We want to kind of take a look at those things because that's also going to tie in later in the day. So really you're just looking at the overall picture when looking at this. When it comes to your QPF, this is telling you how much liquid precipitation or liquid equivalent you could get over that course of time period. Now, I'm not going to tell you specific time scale because based on where you go for this information, they all have a different forecasting range. Some places are shorter, some places are longer. But essentially what you're looking at here is if you were to get frozen or liquid precipitation, how much that would melt down to. Then when you compare that with your winter weather, do these two compare? Obviously, if you're going to have snow in some locations, you're probably going to have a liquid equivalency. So are these two different ones matching up? If you see areas where they're not matching up, that might be a question for you to have in the back of your mind, why isn't that happening? Because there will be a lot of times where when your weather information won't necessarily match up from one thing to the next. So it's always good to check back and forth between the two. The next is aviationweather.gov. This site is great for satellite data. The three things that you really want to look for satellite data is your visible, your infrared, and your water vapor. So for visible satellite, you're measuring the amount of solar radiation. So this satellite is looking down at the clouds, and basically what it's telling you is that the thickness of those clouds is going to show you where there's that most moisture. So if you look on your image, see in these areas here, they're a little bit darker. Those are going to tell you that those clouds are much thicker. Now, the one thing to this is that you have an absolutely clear day. You can also see fresh snow because it's going to reflect quite a bit of that energy back. So that's something to look at as well. You might be able to see where it just snowed based on these weather maps as well. And then as you go down and those clouds get thinner and thinner, you're going to different shades of gray. But by looking at this, you can see that you have a system here, but then you have a dry slot here where you don't have as much moisture and not as many clouds. So that then when you go to your next chart, which is your infrared satellite, and this is measuring the temperature of the tops of the clouds, you'll start to see a correlation, and again, you'll start to see where they're matching up. So again, these are showing us the temperature. Now, as you go up in the atmosphere, your temperature decreases. So in theory, your cloud tops are going to be cooler than the cloud bases, and that's what this satellite is looking at. So in these areas, again, we said that these were much thicker than the one prior. Now we're seeing that these are much colder on the tops of them, so we're seeing that there's some significant development there. So we're actually seeing that there's high clouds there. It's not just all low clouds. But then also, again, we're seeing this void where there was no clouds in the other one. Well, we shouldn't be seeing anything showing up on here because there's nothing to be reflected. And then the last one is our water vapor. This measures the highest level of moisture in the atmosphere. So if you have high clouds, that's going to appear the whitest. And then as you go down in elevation, it'll start to get more gray as you go down. But this is also going to show you the moisture. So again, just looking at everything, again, we have that system right here, and we still have that slight dry slot. There's always going to be moisture in the atmosphere, so it won't necessarily be a huge dark spot where it's just completely open, but it's going to show you that all three of these are starting to match up with each other. So that way, when you're looking at your overall systems, you would know that, yeah, when I looked at my surface analysis, there probably was a low pressure system sitting right off of here. So now all of these things are starting to layer on top of each other, but they're all confirming with each other, which means that you're already starting to get a really good forecast for what your conditions might be like. The next thing is NWSNOAA.org, and this is MOS data. MOS stands for your Model Output Statistics, and typically you see the GFS or the NAM. The biggest question I always get is, what's the difference between these two? Well, the GFS is a global forecasting system, and then the NAM is the North American model. So essentially, these two are recording similar things, however, they have different parameters, and the NAM is going to give you a better resolution. The reason for that is that the North American model is literally just looking at North America, where the global model is looking at everything. So for both of them to compute all of that information in the same amount of time, the NAM is just going to have a higher resolution. Now, when it comes to the accuracy of them, that can change. The global scale one might handle better systems than the North American one does because it's not looking outside of North America. So that's why you always want to compare these two things, and that's why in certain cases, the NAM might look better than the GFS does. So it's always good to look at all of them. Now, the MOS data itself, it looks very daunting when you look at it this way, but I broke it down for you. So your first column here is your date. This tells you what date you're going through. The time part is very important because this is in UTC. So now that we are back on daylight standard time, we are 5 hours behind UTC. So if it were 6 o'clock on here, it's going to be 1 o'clock in the morning here in terms of where you're trying to report for. So you always want to keep that in mind. So just because it says 6 o'clock on here doesn't mean it's 6 o'clock for when you're actually looking at the time frame for it. Now the next part of this is your temperature at the surface. So you can see that you have your temperatures rise and fall. So this is from Mount Washington. We can actually see that this morning we had our lowest temperatures, and then they're starting to rise back up again. This gives you a good idea of how those temperatures might react over the course of those 2 days. As for your dew point, this is going to show you as those two numbers get closer and closer together, your possibility of being 100% for relative humidity and having clouds form. Now the important part here is that you'll notice on the next part that I get to, but you then have the clouds below. Now on the summit of Mount Washington, anytime that our temperature and dew point are within 3 degrees of each other, it's safe to say that we're going to be in the clouds. And we know that because we've been looking at this every single day and taking that information into account. So if there's a particular area that you go to for backcountry activities and you start to see a pattern developing like that, that's great because those patterns will develop just like it does on the summit of Mount Washington where we know that within those 3 degrees we're always going to be in the fog for the most part. So the next part, again, is sky cover. So as those two start to come together, your possibility for clouds is going to increase. So if you have your temperature and dew point closer together, possibility of more clouds, so overcast. Whereas over here, where they're much further apart, you might have few or broken day for that. Next one is wind direction and wind speed. Your wind direction, you just add a 0 to the end of that, and that's going to tell you what the direction is. These are rounded to the nearest tenths of degrees. And then for your wind speeds, this is always in knots. The really nice thing about Google these days is that you can literally put knots to miles per hour into the search bar, and it will bring you to this awesome conversion table. All you have to do is type in your knots right off this table, and it'll automatically convert it for you. So it's really easy to look at. But again, this is for Mount Washington, so you can see that we have those higher wind speeds. But the reason why I chose this, not only because it's more everywhere, but because there are going to be other places as you go up in the atmosphere where winds will increase. So that's something that you always want to be careful with. The next is your possibility of precipitation. These are called the POP6 and POP12. The POP6 is a 6-hour period ending at that time. And then the 12-hour period is the same, just for the 12-hour period. This is going to tell you just your possibility of precipitation. So for instance, yesterday we had a possibility of precipitation of 38%. In fact, it did snow on Mount Washington, so we can actually go back and quality control check and say, yes, that did happen. Then for your quantitative precipitation forecast, this is liquid equivalency. So again, this is in terms of all of your frozen and all of your liquid precipitation that you might be receiving. And they will start to match up along here in terms of, we didn't have much snow, but we did have some, whereas these lower precipitations for possibility might not give you much at all in terms of the liquid equivalency that you get out of them. And then last but not least is the type of precipitation at the hour. There's a nice little chart down at the bottom here. Pretty much you have snow, you have freezing conditions, or you have pure rain. So even though, for instance, right over here, this first column area, we had temperatures that were technically freezing, we're still receiving rain on here. And that's because sometimes the air mass itself can still be just warm enough to be producing rain conditions and not snow. So that's something always to look for on these. Now, this is another really cool thing, and this is from the Meteorological Development Lab. This actually takes all of that MOS data and puts it into a visual form for you, which is really, really awesome, because then you're not trying to slog through all of this data here, but you're getting it in this graphical form. Now, that's not to say that the actual text part of it isn't important, because it does break it down a little bit more so you can actually see those trends. But in terms of the graphical model, it gives it to you pretty straightforward, and you can see exactly what's going on. Now the next one I want to bring to you is this is graphical METAR. METAR code I'm not going to go into explaining to you. It's about a 3-book handbook like this to learn METAR code and how to code it, because there's so much that can go on. It's not telling you what you're forecasting for, you're literally coding what's going on outside. So instead there's this wonderful website that does it for you, and it puts it into a really awesome way of doing it. So every single one of these points on here is a data point that collects METAR data or has an observing station. So if you were to scroll over any of these, again I went to Mount Washington, you would get the current conditions for that day, or for that time period it's out for. And this is already taking that METAR code and breaking it down. So you can see what your temperature and dew point are, your winds, visibility, what type of precipitation you might be getting, things like that. Now if I were to click on it further, it brings me into an even more in-depth section, where it actually breaks down all the past METAR code and gives you an idea of what the past was like. So we can actually look by the time codes and see that we had freezing rain and snow. And then as we went further into the day, it just changed over to showers of ice pellets, and then we had freezing fog for the rest of the day. So it's actually doing all that work for us, so that we're not having to actually look at the METAR code itself, which is really helpful. But then on top of that, it has some of the graphical models as well to give you an idea of what's going on. Now the next thing is mountwashington.org. For the local area, this is a great place to go to. And it's not just because I work there. It's because we actually do a good job at what we do. And on top of that, you can get the current conditions right off of our page. Now on top of that, we do something else, and this is our Outlook. Our Outlook is specific for the presidential mountain range and the higher summits, which is very important because even though you can get a text file from the National Weather Service showing you what they think the conditions are going to be, they're forecasting for most of New Hampshire and Maine. So their degree of accuracy is going to be a little off just because they're trying to forecast for such a bigger area. Whereas on the summit, we're literally just trying to forecast for Mount Washington. But again, this is what the METAR code would look like. So instead of that, you have the slide previous to show you what it breaks down to. So the other thing that we do is a regional forecast. This comes out every single morning. The regional forecast has a couple important things on it. We have our valley forecast, which is located on the top right up here. We then have our summit outlook, which is for today, tonight, and tomorrow, which is right in here. We have the ARVP and yesterday's data. So the ARVP is important. This is the auto road vertical temperature profile, because we actually have a set of mesonet sites up the auto road that tell you what the temperature is as you go up in altitude, which can be very important. So that's what these numbers are right here. This breaks it down by their elevation and then what the temperature is. The other part is yesterday's data. You want to know what happened yesterday, you want to know if you had any new snow, things like that. This is where you'll get that information from. It'll also tell you what your min and max temperatures were. So if you had a maximum temperature yesterday that was above freezing, you'd know that there might have been some snow melt overnight or during that time period. And that'll give you some points to then look at when you're actually doing more investigation. This is the auto road vertical temperature profile. Again, these are the sites along that corridor here. If you were to click on them, you can also get other data besides temperature itself. But then on top of that, we also have our regional measurement sites. This is only a couple of them that's shown on here, but we have other sites set up all throughout the White Mountains, so you can actually get a much more regional picture of what's going on in terms of your temperature and relative humidities as well that will play into your planning. And then we have the Mount Washington Avalanche Center. Again, they're the ones that are helping us out every day in the backcountry. Now they use the weather observations and they actually put it right into their descriptions down here. So even if you weren't ever able to look at a website in terms of meteorology, you'd be able to go to their website and at least have a small idea as to what's going on, because they look at that and they scrutinize that data to be able to put this forecast together. So even if this was the only thing you could go to, it's still a good idea to go there and check out what the weather conditions are. And then lastly, avalanche.org. If you click on any one of the points on here, it will take you to their home site, and every single one of them will have weather described out in their forecast. But then they also always have links to local weather places that you can look. So they might have the actual local National Weather Service page pulled up for you, whereas the ones I showed you, you could go to anywhere in the country and really be able to find everything. So now we've done our homework at home, and we've got all of our stuff put together. We know what our forecast is supposed to be. Now we want to get out in the field. But now we need to know how our forecast is changing based on what we saw at home, based on what we're observing now. So a few things to look at are your sky, your temperature, and your wind. So for sky cover, sky is broken down into octets. We have them broken down into 8 sections. And so based on how much of that sky is covered, that tells you what your sky cover is. So if you have anywhere between 1/8 to 2/8, you have few clouds. 3/8 to 4/8 is scattered. 5 to 7/8 is overcast. And then if you have 8/8, or sorry, that's broken. And then if you have 8/8, that's overcast. And then if you're completely in the clouds, you're considered to be obscure. So on the summit of Mount Washington, that happens a lot for us. We're actually inside of that cloud. Now in terms of determining these things, there's a couple little things you can look at that are really helpful. So the first one is our celestial dome. If we break this down, straight overhead would be 90 degrees. That's half of the sky right there. If you broke that down in half, you'd have 45 degrees. And then if you broke down those sections even more, you'd have about 25 degrees. So one really cool way, and this is actually pretty accurate, to be able to stand in the field and figure out if your cloud cover is increasing or decreasing throughout the course of the day without knowing actually if you scattered or otherwise, you actually take your hands and you hold it out in front of you, and if you were to do this and kind of cover up the area this way on your celestial dome, that would be 1%, going all the way through 25%. So you can actually take a look to see how much of that is being covered throughout the course of the day and whether it's increasing or decreasing cloud cover. Now the other part of this that you can use is just percentage-wise. If you just look at that whole entire celestial dome and figure that's 100%, half of it would be 50. You can then also use the table that's here to figure out what they are. Now they have isolated here, but that would be considered few for every other thing. Now in terms of what cloud cover can tell you, this is a cold front. So in a cold front situation, if we are standing at the star, we are clear above us, but as that cold front approaches us, we're going to be mostly clear until all of that sun and that cold front passes over us, and we're going to see an increase in clouds pretty quickly. So if we start our day with no clouds and all of a sudden we have this front come through, it feels a lot colder, things like that, mentioned down in here, we can help to tell ourselves that that's when the cold front passed. Now, why this is important is because during the morning when you looked at your synoptic information and you looked to see what might be going on over the course of the day, if you didn't think that a cold front was supposed to come in through until the evening, but all of a sudden you saw this change around 3 o'clock in the afternoon, well, your weather pattern is actually speeding up. So you now have to take that into account because maybe the conditions behind the cold front, you were expecting to be already out of the field back at your car, but now you're still in the field and that cold front has already passed. So that's why it's important to still understand when these fronts are passing you. Now the next part is a warm front. This is slightly different. Warm fronts start with high clouds, and that's because you're essentially in a colder air mass and your warm air is riding up over the back of it. So your day would start off with these high clouds, and as the day progressed, those clouds would get lower and lower and lower, and ultimately probably get precipitation out of it right in front of the warm front here. But again, that's important to know based on how fast that front is moving through. Next is precipitation. Now, Mount Washington is notorious for our winds, which means that we are horrible at getting precipitation. Because if you've ever tried to catch a snowflake at 80-mile-per-hour winds, it doesn't work well. So we actually use what's called a snowboard. We actually hold a board with felt into the wind. By holding it kind of sideways, we actually collect those snowflakes. Now, the only way that we can tell sometimes if it's snowing or if we're blowing snow is by looking at snowflakes like this. If we're catching full snowflakes, we know that that snowflake fell out of the sky, didn't hit anything else, and miraculously made it to our board. But if we have all these halved pieces, yeah, they might be falling from the sky and they're hitting things on the way, but it also could be blowing snow as well. So if we have absolutely no full snowflakes, it's usually safe to say that it's not actually snowing, it's just blowing snow. So for our purposes, it's very important to be able looking at those two things. But you might also find yourself in an area where it's windy, just hold out your glove and try to catch snowflakes that way, and it'll help you to determine what's going on. Next is blowing snow, like I mentioned. Now, blowing snow is a little tricky because it's coded differently for METAR. For METAR, blowing snow is considered when it's raised off the ground by 8 feet, which means that it's really windy outside. Whereas drifting snow is if it's lower than 8 feet. So you might be in the backcountry and you have more drifting snow that's going over something, whereas you look up onto the ridge lines and that's where you can see the blowing snow that's being picked up really high above that. Now, blowing snow can tell you a couple things. It can tell you the direction of the wind. If you were to look here, our wind is coming off this way. Now, this is also going to show you that that snow is going to deposit itself downwind and on the leeward side of objects. So if you get into the field and you weren't necessarily expecting a certain wind direction that day, you can look to see where that's depositing and then also make decisions based on that as well. And then this is also some of the other coding that will go into it. If you were to look through the Snow, Weather, and Avalanche handbook, that's the coding that they use. Now, temperature, this is also something really important. We want to know the temperature of the air, not the temperature of the object being heated by the sun. So in this picture, that's why I picked this. It's showing that it's pretty warm, but that dial right there is really in the sun. So it's actually showing the temperature of that instrument, not the temperature of the air around it. So you want to make sure that you're in a shaded region when you get air temperature, but then you also want to make sure that it's not super close to the ground, because the ground can cool things up or heat things down. So you really just want to get a decent idea of what that temperature is. And you might see these in different areas. This is called a Stevenson screen. This is where our minimum maximum thermometers are located. So usually if you see one of those, it's probably a good place near there to find out where your temperature is, because they're somewhat in the shade sometimes. And then also when reading them, just always make sure eye level and reading at the bottom of the meniscus. Some temperature hints from rime ice. Rime ice forms because super cold water droplets freeze on contact. Now if you have a cold front that's passing, you have slightly warmer temperatures to begin with. Those particles are going to hit something and they're going to freeze, except freezing a little bit slower. So because they're freezing just a little bit slower, air has time to escape. When that air has time to escape, it actually makes this clear ice. Now, as that cold front passes and your temperatures get colder and colder and colder, those water droplets start freezing faster and faster and faster, which doesn't allow that air time to escape. So essentially what's happening is that you're going from where you have warmer air down to where you have colder air, and it's trapping that air inside. Now, this doesn't work all the time, but if you come to an area where you do have rime ice, this is something you can look at to see if there was that temperature drop over the course of it. And again, rime ice forms into the direction of the wind. So the place closest to where it originated from on a coast is going to be the oldest. Moving out towards the end of it would be the newest. And then lastly, we have wind. You can use different types of scales to determine what's going on outside. One thing to remember is that this was not designed for winter conditions. This one here has a little bit more of it kind of worked into it in terms of being able to have snow drifting and determining where that would fit in. But always take that into account. Just because you can't see trees moving doesn't mean that they wouldn't be able to move if they weren't weighed down by snow. So it's just that one extra little thing you need to take into account. But again, this gives you something in the field to know that if your winds were supposed to increase throughout the course of the day, to kind of know how much they actually are increasing. But then also just having a really nice handheld anemometer in the field is a really good thing. And then in terms of force, this is probably one of the most misunderstood things when it comes to wind. When you double the speed of wind, it actually quadruples the force. So when you're standing outside and you think it's 40 miles an hour, it might really only be 20 miles per hour. The best way to explain this is that 10 mile per hour winds was one linebacker hitting you. 20 miles per hour would be 4 linebackers hitting you. So even when you're out in the backcountry, the wind might be significantly less than what you actually think it is just because you're not used to the force of it. So just keep that in mind as well. Wind direction, again, rime ice forms into the direction of the wind. So in this particular case, our wind was coming from this direction, and it was forming that right there. Another way to orient yourself is if you have a map with you, find out where a certain direction is and feel where the wind is coming from. If you weren't expecting the wind to come from a certain direction, and you're planning to be right in the leeward side of something, you might want to take that into consideration if you've had blowing snow and winds depositing lots of snow into that area. And lastly, if you're going to be kind of above tree line, crumholts are great. They're really great because they tell you the typical wind direction. Crumholts grow this way because all of the wind comes from this direction, typically snapping all of the branches off in here, so they've just learned to grow with the direction of the wind. So if you know that a particular day you go up onto a slope and the wind is not following what those are, you can tell that your conditions for that day are going to be different than what it typically is. So if you've gone out every other day of the year and had no problem, but today all of a sudden your winds are 90-degree offs, well, your conditions aren't going to be the same from what it normally is in that terrain. So now we just kind of tie all this together. The biggest part is just going home and researching different things, knowing the fact that weather is constantly changing, and we're constantly learning more about weather. Weather as a science is relatively new. Our significant discovery really didn't come until almost 40, 50 years ago when we were actually able to start putting it together. And as they were mentioning earlier, it has a lot to do with technology. Because a lot of our weather is based off of forecast models that are run through a computer, we can only forecast as well as we can have a computing power to do it for us. So it's always going to be changing. So this is one of those things that every year when you come to a workshop like this, always refresh yourselves on new things that have come out in weather. Maybe pick up a couple papers and look at what they're doing, because that'll ultimately help you to understand it before you even get into the field. And then further, once you're out in the field, just be aware of what's going on around you. Like I said earlier, you guys are all observers. You've all observed if you needed a jacket or sunglasses on a particular day. So even just doing those simple little observations in the field can make a huge difference when determining what you saw at the beginning of the day versus what's actually happening over the course of the day and how that's going to change your decision making. And the other thing is, before you go out, you make conditions for yourself as to, well, if I get to this point and something happens with the snow stability, I'm going to turn around. Do that with weather too. If you don't feel comfortable being in higher winds when you're traversing or something like that, make those turnaround points for yourself. If the wind increases too much, I want to make sure that I turn around, or I want to make sure that I reassess what my route is at. So weather really does play a big part. Again, it's one third of that entire observing portion. So, questions?